Welcome everyone to class number 10. In this first video we're going to look at what causes wind, and this is part of our sequence on Earth's energy budget and renewable energy. So in recent videos we've looked at energy transfer between different heat reservoirs on Earth. In the last video we looked at solar insolation and how wind and clouds arise from differences in solar insolation. And today we're going to take a closer look at specific types of wind that are commonly used to generate electricity. And then in the video after this, we'll actually look at some of the fundamentals of renewable electrical generation, like solar and wind. So why is this important? Well, in my view, it's important because wind energy is a growing and controversial topic. And it's important to understand why each state and each location has a different potential for wind energy and where that arises from. So before we get started, I'll just make the point again. Wind and solar are both forms of integrated nuclear power. The nuclear fusion in the sun releases photons, which can then be directly harnessed as solar power. Or in this case, those photons will go and heat the land surface. They'll drive changes in air pressure between hotter and cooler parts of the surface, which of course that air pressure gives rise to wind. So really we're actually harnessing nuclear power when we harness wind energy, but it's been processed through Earth's energy system. So to motivate this a little bit, here's a map of wind electrical generation potential in the United States. And it's fascinating to look at this distribution and think about why it looks this way. So the thing that really catches your eye is all this great, very windy areas in the Midwest, just on the east side of the Rockies. But then we also see bands of wind in other places that are really associated with topography, like mountain ridgelines in California and also mountain ridgelines in New England. So we're going to look at what causes these differences in wind potential and average wind speed. So the outline for the video, we'll look at those three major types of wind. That's coastal wind, Venturi effect, and katabatic winds. And then we'll talk a little bit about surface roughness and laminar flow. So recall from the previous video that wind is just air flowing from high pressure to low pressure. So cold, dense air weighs more and creates high pressure, which squeezes the air out from under it, and it flows off towards lower pressure. So all wind is created by air pressure gradients at the surface. So really what we're going to look at now is where can we find consistent air pressure gradients. And the first place is along the coast, and these are called coastal winds. And the idea here is that land and water have very different heat capacities. Land has a low heat capacity, so it changes temperature really easily between day and night. Whereas the water has a high heat capacity, basically doesn't change temperature between day and night. So what does this mean? It means during the daytime, the land warms, and we get low pressure as that warm air rises up, and cooler, dense, high-pressure air flows in off the ocean, okay? So during the daytime, at least in the summer, you'll often get an onshore wind as high pressure builds over land, as low pressure builds over land during the afternoon. Then at nighttime, it's the opposite. The land cools down really quickly, actually ends up getting a little colder than the ocean, so that air sinks as high pressure and then flows offshore towards the lower pressure air over the ocean. So at night we get an offshore breeze. So basically the pressure gradient is changing between day and night, and we're getting a breeze in opposite directions, but the important thing is that wind is consistent. It's frequently blowing. So an example of an offshore wind project is Horseshoe Shoals in Nantucket Sound. This project looks like it's been defeated now, but it was on the books for many years. And the idea was to put 130 wind turbines kind of right here, right in Nantucket Sound. So I think this is the coast of Massachusetts. This is the island of Nantucket here. And 130 large turbines. These were going to be big offshores. The total capacity was going to be about 454 megawatts, but running at only about 37% efficiency, which would give you an annual generation of about 170 megawatts. So we'll see later that's a lot of electricity. And one of the questions and criticisms of this project was that wind can be unsteady, that we can't rely on wind during times of peak demand. And so the developers looked into that question. And if you think about when times of high demand are in New England, it's in the summer, on the hottest summer afternoons, when people start cranking up their air conditioning, sucking down the electricity. So some test turbines for this development showed that if you look at the 10 times of peak electrical demand in New England, of course they're all on summer days in the afternoon, what they found is that the wind was always blowing pretty darn fast in Nantucket Sound at those times, and the estimated wind production would have been well above average during those peak times. So and that's because of this coastal wind effect, right? When it's hottest on land, that's when we get the lowest pressure air rising up and drawing the onshore winds from the ocean onto land. So in this case, coastal winds were actually going to be pretty effective because they tend to be strong on hot summer days. Okay, so let's take a look at the second type of wind now. This is what we'd call Venturi winds, or the Venturi effect. And these are winds that are concentrated at ridgelines and through mountain passes. And the way this works is fairly straightforward. We have usually areas with a dominant wind direction. So in the United States, this is often areas with westerlies coming off the Pacific Ocean in the west coast, or even westerlies in Vermont. And as that dominant wind flow is coming along and it meets a mountain range, the air is forced to compress either laterally through a mountain pass, but also compress vertically over a ridgeline. And so here we need to think of wind as being a fluid, basically. And this is the same effect as if you put your thumb over a garden hose, right? The flow of water coming through that garden hose is forced to go through a smaller opening, and tends to go through that opening much faster because the pressure behind it is still constant. And that's really the idea here, is that this dominant airflow is bringing kind of a constant forcing pressure with it, and then when you compress that air through a smaller space, it has to go faster to get through, and then we can make wind at mountain ridge lines and passes. So a good example of this is the west coast of California. Here's San Gorgonio Pass. This is located just east of Los Angeles. So here's the Los Angeles basin over here. Westerly winds are coming, and they're being forced through this mountain pass, San Gorgonio Pass. And if you've ever driven the highway through here, there are hundreds of wind turbines laid out on the other side of this mountain pass. And those consistently westerly winds are forced through the pass, they accelerate, and they make lots of wind energy here. So the third type of wind is called katabatic wind. And these are winds that are generated as large air masses are forced up and over very large mountain ranges. So these are different than the ridge lines or mountain passes we were talking about. These are things more of the scale of the Rocky Mountains or the Himalaya or the Andes. And what happens is that wind, that air pressure, forces the air up and over the prevailing winds. And as the air masses spend time up high above the mountains, they cool down and they condense and they become high pressure air masses. Then they make it over the other side and they end up flowing down towards generally warmer, lower pressure air down on the flats on the backside of the mountain range. So you basically get this high pressure cold air rushing off the backside of the mountains, and that's called a katabatic wind. So those are the three types of wind. Let's switch now to finish up with surface roughness and laminar flow. One thing to consider is that wind is basically a fluid, and if in ideal cases it flows along by laminar flow, where layers of the wind basically flow past each other at different velocities with relatively little friction between the different layers. So that's called laminar flow. Now, if you put an obstruction in the way, like a tree or a house, the wind has to go around it, of course, and so these flow lines get disturbed, and then we get what's called turbulent flow, where we get wind going in all different directions, sometimes directly opposing itself, and we end up with this chaotic situation with a lot of opposing currents and a lot of friction, and that slows the wind down quite a bit. So that's called turbulent flow. So obviously the difference here is roughness on the ground. Places that have smooth surfaces, like the ocean, tend to have great laminar flow. Places that are rougher, like urban areas built up, tend to have more turbulent flow. And so in this example, you can see these plots of wind speed as a function of height. So here, wind speed's increasing. At 150 feet, it's only 61, whereas over the ocean at 150 feet, it's already 91. So you can see that wind speed increases a lot more over the open ocean because you get this nice laminar flow. You don't get the turbulence. So just to put a visual example on that, these offshore wind turbines can actually be made to be quite a bit lower over the ocean than they would be over the land because there's no roughness on the surface disturbing the laminar flow. So they don't need to be as high to stick up into the fastest wind speeds. In contrast, if you've got a little turbine outside your house and you live in the woods, well, the wind's not going to blow very fast because there's all kinds of turbulence based on those trees and buildings. So I'll synthesize all this with the map we looked at in the very beginning. This is the electrical generation potential from wind in the United States. And what we can see now is that this huge area on the east side of the Rockies is very windy because of katabatic winds that are flowing off the Rockies here, okay? Then we can see examples of the Venturi winds all over the place. Note that the best wind electricity traces the ridgelines all through New England, also traces a lot of the ridgelines in Southern California, and also in the Pacific Northwest, and the Rockies actually. And then of course we can see the coastal winds in some places, like here on the coast of Texas, where there's some decent wind potential based on those onshore, offshore winds. So I'll leave you with this concept question, a link to the quiz, and join us for the next video, and we'll talk about how to generate electricity from wind and sun.